Hello everyone, welcome back once again to the JCE Connect. I am Naresh Patil, working as assistant professor in Jain College of Engineering, and today I am here to discuss a design problem over a built up compression member or a built up column in steel structure. Okay, so in my first lecture of design of compression member, I told you the types of sections used as compression member in steel structure, that is standard rolled eye sections, channel section, or section made up of plates, angle sections. Okay, so those are all rolled steel section which are standard section, and sometimes it is a necessary to design built up column section also. Okay, so built up section is made up of generally 2 3 or by using the number of standard rolled sections or plate sections. Okay, so generally built up sections are like 2 eye section, 2 channel section placed face to face, or 2 channel section placed back to back, or 4 angle placed at the corners. So on we have the different types of columns also, built up columns. Okay, and today I am here to discuss about how to design built up column consisting of 2 channel section placed back to back. Okay, so I'll read out the statement of the problem first. Okay, so here it is given as design a built up column consisting of 2 channels placed back to back so as to support a factored load of 1600 kilonewton. The length of the column is 18.5 meter. Okay, and it is fixed at both ends. Okay, I'll read out once again the important data. So we have to design a built up column consisting of 2 channel sections placed back to back, and they have to support a factored load of 1600 kilonewton. The length of the column is 18.5 meter and it is fixed at both ends. Okay, so quickly I'll just note down the given data. Okay, so the given data are here. First of all, the length of the section is given as 18.5 meter. Okay, and the end conditions are both ends are fixed, both ends are fixed. Okay, then so therefore effective length LE is given by, when the both ends are fixed, so it is K into L. So when both ends are fixed, K value is 0.65 into L is 18.5. Okay, so that is 0.65 times L, 18.5. So we'll get this as 12.025 meter. Okay, so that is LE, the effective length of the column. And as I told you, the as per IS 800, when the both ends of the columns are fixed, the effective length factor K is taken as 0.65. As per IS 800 2007, I am repeating again, the effective length factor K is 0.65 into the total length, that is 18.5. So we will get the length of the column as the effective length as 12.025 meter. Okay, so now assuming allowable design compressive stress, assuming allowable design compressive stress for built up section. I told you, if you remember, so we can consider it is 140 Newton per mm square. We'll assume it is that is allowable stress sigma 140 Newton per mm square for built up section. Okay, so therefore area required is equal to Pu divided by this thing. Okay, stress, force divided by stress, so that is 1600 into 10 to 3 divided by stress is 140. So it is 1142.8.57 mm square. So we required area. So I'll check once again. So it is 1142.8.57 mm square. Okay. So we have to design built up section consisting of two channels placed back to back for area more than, this is by thumb rule we have got, more than 11428 mm square. Okay, so I'll just note down, I'll just give a note here. Note, we need to design a built up section considering of two channels placed back to back, Okay, so we need to design a built up section consisting of two channels placed back to back. Okay, so therefore area required, area of channel required, therefore area of channel required is 1142.8.57, okay, 57 divided by 2, because we have to provide two channels, so we can easily find out for area for a single channel. So we'll get 5714.25 mm. Okay, so this is, we have to select a single channel of area more than 5714.25 mm square. Okay, now you have to refer steel table and you have to find out a channel section, single channel of area more than 5714.25 mm square. Okay, so now we'll refer the steel table here. So now you have to refer steel table. Okay, now if you open, okay, so here you can check the channel section. Okay, and here it is given rolled steel channels, and here dimensions and properties. Okay, so what you have to do, you have to go here, first of all designation, then after that this is weight is given. Okay, so after that one more important is sectional area. So for selection of channel section of our area required, you have to go and referring the areas. Okay, now you have to refer from this. Okay, so by referring this, I have selected ISMC 400. I have selected ISMC 400 at 49.4 kg per meter. I have selected for my solution ISMC 400 49.4 kg per meter. Okay, and for that the area is 6293. For that I have selected for higher side for safety. Okay, so that is we have got the area as 6293, means 6293 mm² for single channel, and our area, the required area, we have, as per the thumb rule, we have what it is 5714, and we have selected 6293, which is more than this. So for safety we have selected higher area. Okay, so I'll note down. Okay, so from steel table, choose 2 ISMC 400 at 49.4 kg per meter. Okay, so therefore area provided is equal to 6293 into 2, because we are going to provide 2 channels. So 6293 into 2 channels, so we will get 12586 mm². Okay, so the area provided is 12586, and I have drawn a sketch here. You can see a 2 channel sections placed back to back, 2 channel section placed back to back. Okay, so here we have to find out the spacing. What should be the, we have to place back to back, but we have to find out what should be the spacing between these two. What should be the spacing? So that is S. Okay, spacing. So what should be the spacing between these two? That we have to find out first. So for that you will note down the other properties. Okay, I'll note down the other properties. So here, according to the selected section, we have got IXX is equal to 1508.8 into 2. So because 2 channel sections, we will get 30165.6 mm². Sorry, mm raised to 4. Sorry, mm raised to 4. So we have got it is 15082.8 into 2, that is 30165.6 mm raised to 4. Okay, actually I can show you here. We have to find out IXX. So for built up section, we have to find out the moment of inertia I, that is I is equal to, that is by using the basic formula I self plus AH square. Okay, this is the basic equation, but in moment of inertia about horizontal axis, that is XX, what will happen here, the value of H, this H is equal to 0 about horizontal axis, that is XX. About the XX axis, the value of H is equal to 0. So A into S square will become 0. So only, that is I self, that is 15802.8 into 2, because for 2 channel section, that is I is 15082.8, because this term will become 0. That's why we are not multiply A H square. So why H is 0 here? Because if we see, this is the horizontal axis and with respect to the horizontal axis, okay, this is our the horizontal axis of the built up section or the whole section, and our CG or the CG of the channel section is also in same plane. The CG of channel section is also in same plane about horizontal axis. So both axes are coinciding here. So automatically the h will become 0. So because of that, what will happen? A into h square, this term will become 0. So we have to calculate only I is equal to I self, that is 15082.8 into 2. So that is 30165.6 mm raised to 4. Okay. So this is regarding I xx. Okay. Now same way we have to find out moment of inertia about y axis. Okay. Moment of inertia about y axis. Also moment of inertia about y axis we have to find out. Okay, about y axis. Now here again one more important is about y axis. Okay, about y axis, the moment of inertia is again depends upon the spacing between two channels. What is the spacing between the two channels? Okay, so the moment of inertia about y axis, I repeat once again, the moment of inertia about y axis is depends on the spacing between two channels placed back to back. Okay, so for that we have to find out the spacing between two channels first. What you have to find out? We have to find out the spacing between two channels, so that to get the moment of inertia about y axis. So how to get that? Okay, how to get that? That is very important. So we will do one thing. So therefore here equate, we will equate Ixx is equal to Iyy. We will equate Ix is equal to Iyy. So we know that Ix is equal to, already we have got 30,165.6 into 10 raised to 4 into 10 raised to 4 is equal to moment of inertia about y axis. So that is again I plus a h square, I plus a h square. So I will calculate here. So here what is I plus h square? Again it is moment of inertia about y axis for channel section. So if you refer, so we will get, okay, now if you refer, if you want I will show you here if it is possible. Okay, here I can show. See, this is the moment of inertia about y axis. So that is 504.8. Okay, so that is 504.8. So 504.8 into 10 to 4. So that is I plus a h square plus area is 6293 into h is s by 2 plus 24.2 whole square and again into 2. So I will explain one by one. So as I told you, this is I is 504.8 into 10 to 4, that is the moment of inertia of channel section about vertical axis. Then I plus a, area is 6293 for single channel. Then the spacing is s by 2. So that is h is a into h square. So s by 2 into 24.2. Okay. So I will come back to the figure. Okay. So here I want to find out the h distance from here to here. I will just note down that. So I want to find out the h distance, this. I want to find out this h distance now about vertical axis. Okay, I want to find out the h distance about the vertical axis. So here the h is, we can see here, from here to here it is s by 2, because total is S, the gap between two channel section. So this is S by 2 and this is H. Okay, sorry, not H. So this value is 24.2. This value is 24.2. So this value will get it again from steel table. So S by 2 plus 24.2, that is nothing but H. Okay, so H is, we can see S by 2 plus 24.2 whole square, A H square into 2, because two channel section. Okay, so I'll show you where you will get 24.2. Okay, now if you see here, this value is nothing but CYY. CYY, that the distance, that is, you can see the distance from CG to the face, distance from the CG about vertical axis from the face, so that is CYY. So that value you will get it from CYY. So I can show you here. Okay, so this is CYY is 24.2. I can show you, you can see here CYY, it is 24.2. It is 24.2. Okay, so that's why I have taken H is equal to S by 2 plus 24.2 square into 2. Okay, so from this we have to find out the value of S now. Okay, the value of S. So I'll just explain the steps how to get the value of S now. Okay, so here, so I'll note down here. So that is, I'll 6293 into S by 2 plus 24.2 square into 2 is equal to, I'll minus 504.8 into 10 to 4 from 3016.3016.5.6. So 3016.5.6 into 10 to 4 minus 504.8 into 10 to 4 into 2, because 2 is for two channel sections again. Okay, so here now, so we'll get this value as 291.56 into 10 is to 6. Okay, 291.56 into 10 is to 6. Then again here S by 2 plus 24.2 whole square is equal to, I'll take again from this to this side, so 291.56 into 10 to 6 divided by these two, so 2 times 6293. Okay, so this value will get it as, this value will get it as 23.165 into 10 to 3, 23.165 into 10 to 3. Okay, so now we have S by 2 plus 24.2 square, this side 23.165 into 10 is to 3. So we will get S by 2 plus 24.2 is equal to square root of this, so that is 152.20. I will check once again. That is square root of 152.20. Okay, so therefore S is equal to, we'll get it as 256 mm. So I'll round figure to 260 mm. So that is face to face. Okay, so from this we got the spacing between two channel section. Okay, this we got it as 262, sorry 260 mm. So we got this answer as 260 mm. The spacing between two channels as 260 mm. Okay, understood? So we will calculate IYY because as we got the spacing between two channel as 260. So therefore IYY is equal to 504.8 into 10 raised to 4 plus 6293. So 260 by 2 plus 24.2 square 2. So we will get this value as 309.361 into 10 raised to 6 mm raised to 4. Okay. So we got IYY. So therefore I can write I minimum is equal to, again it will be list of IXX and IYY. So I minimum is equal to, we have got it is IXX. So that is 301.65 into 10 raised to 6 mm raised to 4. Okay. So we got IYY as IXX as I minimum. Okay. So therefore slenderness ratio lambda is equal to KL by R minimum. Okay. So what is R minimum again? So therefore R minimum is square root of I minimum by area. We cannot use directly R minimum from steel table for channel section because it was given for single channel, and here we have used two channel sections. Okay, so that is I minimum by area. So I minimum is, we have got it as 309.361 into 10 to 6 divided by area as 2 times 6293. So we got R minimum is equal to you will get R minimum is equal to 154.80 mm. R minimum is 154.80. So therefore lambda is equal to KL by R minimum. So we have already calculated KL. So that is 12025 divided by 154.80. So that is 77.68. So that is the slenderness ratio is 77.68. Okay. Now from page number 48, clause number 7.6.1.5. okay, if you go to page number 48, the clause is given for slenderness ratio of build-up column. Okay, I'll just show you that. So you can see the build-up columns are like this. That is single lacing, two sections with single lacing, and again double lacing, two section with double lacing. Again we have here double lace and single lace combined with crossbars. So this is the cross numbers with double lacing with cross plates and a single lacing with cross plates, okay, like this. And here we can see in the plan, so here the two channel section placed face to face, not back to back. Here you can see AB, AB, and these are the two channel sections placed face to face, not back to back, okay. So for this, again, as I told you, if you go to page number 48, if you go to page number 48 here, I'll just show you. One minute. So you can see here, okay, it is given as this is for 7.6 laced column. You can see laced column, and if you come here, 7.6.1.5, the effective slenderness ratio KL by R of laced column shall be taken as 1.05 times the KL by R, okay. So the effective slenderness ratio KL by R we have to consider for laced column, that is 1.05 times the KL by R actual. So 1.05 times the KL by R actual, the maximum slenderness ratio, in order to account for shear and deformation effect. So we have to take the actual the slenderness ratio, effective slenderness ratio KL by R effective for laced column 1.05 times the actual, okay. So I'll just show you here how to get that. So here you have to consider lambda actual is equal to 1.05 times lambda, 1.05 times lambda, okay. So this is, we'll get it as 1.05 times 77.68, okay. So that is 81.56. So again, from table 9C, because I told you for built up column you have to use table number 9C. So you got the lambda as 81.56. You have got the lambda as 81.56. Now you have to go to table number 9C, page number 42, okay, page number 42, and we have to find out the value of FCD. We have to find out the value of FCD. Why table number 9C? Because for built up section you have to use directly the buckling class as C, okay. So that's why you have to use table number 9C, okay. So by referring this, we got FCD is equal to 133.66. You have to find and you have to interpolate here, okay. So we got FCD as 133.66 Newton per mm square. So therefore PCD is equal to FCD into AP, okay. So that is 133.66 into area provided is 2 times 6293. So we'll get it as this value as it is, the PCD is, you got as 1682.24 kilonewton, 1682.24 kilonewton, which is more than 1600 kilonewton. So therefore okay. So whatever the selection we have selected, it is safe to carry a load of 1600 kilonewton. So this is the first part we have covered, means the selection of the section is safe, okay. Now next we have to design for lacing, okay. So that I'll covered in next session, okay. That is, next we have to cover design of lacing, because built up column consists of lacing also. Just now I have shown you the figures. I'll show you once again the photographs here, okay. So we have designed the section only. Now we have to design lacing, single lacing we have to design, okay. So when we design for design of lacing, again you have to follow the further clauses or the criteria from IS 800. Okay, that part I will cover in next session. Okay, thank you.